Today's lab is on column chromatography and gas chromatography. So what is chromatography? It's basically a purification technique, and the way it achieves this separation is by taking advantage of the fact that different molecules have different polarities. Now, column chromatography is composed of two different phases: a stationary phase, which is usually silica or alumina, which is very polar, and a mobile phase, which is usually a less polar solvent. Now, gas chromatography also has a stationary phase, but it's and a mobile phase, but its mobile phase, instead of being a solvent, is actually a inert carrier gas. Now, what is common chromatography? It's just a type of chromatography, and it takes place in what we call a column, which is a glass tube, which we place vertically, and we pour the solid stationary phase, which is again usually alumina or silica, into the column. And then onto that solid stationary phase, we add our mixture. And once we add our mixture to the solid stationary phase, we add our mobile phase over it, and the mobile phase will wash the mixture through. And depending on the polarity of the components of that mixture, they're going to separate at different rates, and they're going to make these bands. And in this picture to the left, you can see the column. It's a glass tube. It tapers down to a point, which is where the stopcock is. The stopcock can use to open or close the column, so the element could run through. And that, by the way, the element runs down through using gravity to the end of the column. And these bands that are formed, you could kind of see them in this picture. There's a red band and a blue band. In theory, you want them to be more pronounced, but in practice, they usually look sort of like this. They kind of run a bit. So the process, oh, by the way, you can see what the bands are supposed to look like here in this image, how they're just pronounced sections of compound. So the process is, first you want to pack your column with stationary phase. And in your lab manual, it shows you the steps to pack a proper column. I'm going to kind of gloss over it right now. So you have your column packed with stationary phase. Then what you want to do is dissolve your mixture in some solvent, and then carefully pipette that solvent onto the top of the stationary phase. And it's important to not disrupt the stationary phase. Now, once your sample has been pipetted onto the stationary phase, you're going to add your mobile phase, which is also called eluent. So you're going to add your eluent onto the top, and the eluent is going to drag the components in the mixture down through the column, and depending on their polarities, they will separate at different rates, which will achieve the separation. And we can see in this diagram that that's exactly what happens. First, they're at the top and they begin separating, and the next step, they have already achieved significant separation. And you can see at the top, we have this blue band, which is composed of a polar compound. And we know that because the stationary phase itself is polar. So polar compounds are going to be more attracted to it, so they're going to lag behind in the column. They're not going to travel very far in the column compared to less polar components. So we have this red band, which is composed of a moderately polar compound. And finally, we have this green band, which is composed of a relatively non-polar compound. As you can see, since it's not very attracted to the stationary phase, it's able to freely move down the column. And we just keep adding eluents into the column until one of the bands reaches the bottom, and then we then put a test tube or a beaker or some kind of vessel to collect that fraction. We make sure just to get that band, and then you can go ahead and dissolve the solvent, evaporate the solvent, and achieve pure compound like this. Now it's important to note, I said that in step one, when you're adding the solvent, and when you're adding the sample, not to disrupt the stationary phase. And when you start adding the eluents, it's also important not to disrupt the stationary phase on the top. You want it to be level the entire time. And the reason you want that is because, so this is the first slide that I showed. On the left is a picture of the column chromatography I ran. And you can see the top of the stationary phase. I didn't do a good job at not disturbing it. And you can see on the right side, it kind of dips down, right? So When I added my sample and I added the eluent and began to run the column, and my columns began to separate and my compounds began to separate out, the bands were not even. You can see my bands have like this noticeable dip, where that dip in my stationary phase was on the top. And when you don't have an even stationary phase on the top, your bands are going to reflect that. And this is bad because you can't really see the bottom compound too well, but because of these bands being uneven, there's going to be a section where what I'm getting out of the column is not pure. It's going to still be a mixture. So it's going to affect the yield of pure compound that I obtain. So going back to this, we explained general process. Now the theory behind it. So why? Why is it that these compounds separate at different rates? Because of the polarity. Well, let's take a look at benzyl alcohol here on the right. So this is a very polar compound. And the stationary phase, which we can see here as silicon atoms, this is silica, and they have hydroxyl groups hanging off of them. So what happens is that the polar benzyl alcohol, it's going to experience intermolecular attractions between itself and the stationary phase. And because of that, most of the time it's going to be bound to the stationary phase when it's in the column. Now, when it's bound to the stationary phase, when your compound is bound to the stationary phase, it's not moving down the column. It only moves down the column when it's in the mobile phase. And since the mobile phase is not very polar, and like dissolves like, this polar benzyl alcohol is going to prefer to stay bound to the stationary phase rather than go into the mobile phase and move down the column. So this benzyl alcohol is going to lag behind and stay towards the top of the column. Now in the middle, we have benzaldehyde, which is moderately polar. And yes, it does have some affinity towards the stationary phase, but it also has some affinity towards the nonpolar mobile phase. So it's going to spend some time attached, bound to the stationary phase, but it's also going to spend the equal amount of time in the mobile phase. So it's going to move moderately down the column. And finally, here on the left, we have ethylbenzene, which is relatively nonpolar. It doesn't have any sort of strong attractions towards the stationary phase because it's nonpolar. It's going to prefer to stay in the mobile phase. And because of that, it's going to wash down the column relatively quickly. Now, pros versus cons of column chromatography. Some of the pros is it's a relatively simple setup. If you just think about it, it's a glass tube that you pack with solid stationary phase. You add your sample to the top of the stationary phase, and then you run some eluent through it, and that's it. It's relatively straightforward. And even though it's relatively straightforward, it achieves some very good separation. Very good. But the cons, there are drawbacks to column chromatography, and one of the major drawbacks is it can be very time consuming. Column chromatography can take anywhere between 30 minutes and several days. I've had columns take up to 3 days. But the only saving grace of that is they do take several days, but they separate your compounds very well. And because it takes so long, even though it achieves very good separation, you usually want to try other methods of purification first before you run columns, such as extraction or recrystallization or other things of that nature. And the other con is the solvent system that you need to use to determine, use for the column chromatography is determined by trial and error, and this could also take some time. Now, we're also going to be covering gas chromatography, commonly known as GC. And gas chromatography is just the type of chromatography which takes place in the gas phase. And this is carried out by an instrument called a gas chromatograph. Now, this process involves you dissolving your sample, your mixture in some solvent. And we're talking small amounts. We're talking microliter amounts of solution that you're going to be injecting into the GC. So because of that, gas chromatography isn't really used to separate out large amounts of compounds. It's more of an analytical tool to see how many components you have in your mixture and maybe identify what they are, kind of like TLC. So what you're going to do is you're going to dissolve your mixture, small amount of your mixture in solution, and you're going to inject that into a heated injection port. Once you inject your sample into the gas chromatograph, it's going to vaporize, and a inert carrier gas is going to push it through the column. Now, the separation, the way it's achieved is basically the same way as gas chromatography. The only thing that's changed is that it's in the gas phase. So you're going to have a stationary phase lining the column, and the more polar components in your gaseous sample are going to be attracted to it and lag behind in the column. And your less polar compounds are not going to be very attracted to it, and they're going to proceed further down the column, and this causes a separation. Now the carrier gas is going to push them through the column. They're going to be separated into their individual compounds, and then it's going to go into a detector, which is going to detect the concentration that's coming through, and it's going to feed that information to a computer, and it's going to produce what we call a chromatogram. Now, for the chromatogram, on the x-axis, we have retention time in minutes, and on the y-axis, we have detector response, which is usually like voltage. Usually as the compounds pass through the detector, there's a change in voltage, and that's what it's measuring on the y-axis. And I say usually because not all of them detectors are the same. And as we see here, we have 3 peaks, and the peak at 3 minutes came out first, followed by the peak at 7 minutes, followed by the peak at 10 minutes. And the area under the peak is representative of the concentration of that compound in your mixture. So we know from the chromatograph that there are 3 peaks, and we can kind of tell the ratio of one compound to another, depending on the area under the curve. And we can also identify what they are if we have other spectra to compare them to. So this is kind of like an analytical technique, like I said before, like TLC, while column chromatography is used to separate, I don't want to say large amounts, but relative to gas chromatography, it's a large amount. It's like on the gram scale, like 2, 3, 4, 5, maybe up to 10 grams. Now you could use it to separate out more compounds, like a larger mass of mixture, but the more amount, like the bigger the amount of compound you're trying to separate, the bigger the column needs to be, and it gets to the point where you have so much mixture that you're trying to separate that you need an enormous column, like so big that you need to climb up a ladder in order to add it to the column or to add some element through it, and it just becomes impractical. So that's it. Here are my references, Chem Survival. I'll be sending you these videos. Okay, guys, have a nice day.